Hello, my name is Brian, and I'm here to hack on Tiger Beetle. So this is the stream where presently I am working on creating the Rust client for Tiger Beetle, the financial database. And I am doing this whole project front to back, all on stream. So if you follow along over many weeks, you will see the creation of an entire Rust project, warts and all, many, many mistakes and all. I hope it is going to be interesting and useful. So recently, we've been working on creating the request methods, the async request methods for all of the requests possible in Tiger Beetle, which is the bulk of the project. And we finished getting one working, like functionally complete, as far as we know so far. And we're about to continue on with the rest of the requests supported by Tiger Beetle. So last time we realized that we had made a mistake with our design. So we created a method for looking up accounts, and lookup accounts is the easiest type of request in the database. We created a method to look up accounts, and this method allowed you to look up one account at a time. And it worked. But the problem is that the Tiger Beetle, underlying Tiger Beetle library for clients, there is a single library called TB client that all the clients for other languages bind to currently. The underlying client supports submitting multiple requests of the same type at the same time for efficiency reasons. And we realized that late. So we had to go back and kind of redesign and explore a little bit about how the client code really worked. And at the end of the last stream, we had a working account lookup that worked for multiple requests at a time. And we ended the stream on a bit of frustration because I wanted to ensure that our async functions didn't capture the lifetime of one of its arguments. Because just thinking about the interface that we really want, every lifetime you capture, especially in an async function, is going to cause like some kind of problems for some caller. Because in our case, it meant that they were going to have to hold on to a buffer with the original request for the entire lifetime of the future that they're waiting for the request result on. And that, to my mind, at this moment, given what I know, I think is going to be undesirable. So we were trying to express this in the type signature of our request method that, you know, this buffer being passed in, we don't want to hold on to a reference to it. And frankly, it's been a while since I've done async Rust, and I've never, understood it deeply. But we spent, a half hour, 45 minutes, like just trying stuff, and then also looking at docs together online. And ultimately, we failed, but it was an adventure. So today, my goal is to go solve that problem. I went and read some of the Rust documentation, refreshed myself on how Rust futures do captures and how async functions desugar, and now I'm pretty sure I know the right formulation we need to express this in the type system. And we're going to go fix that. And then once we have that query, the account lookup query working to our satisfaction, we're going to go move on and revamp one of the other methods that we've already written to make it follow that same pattern and support multiple operations, multiple requests at the same time. And if we get through that and we still have energy, I would like to just kind of step back and look at our API that we've designed so far, which is very rough and ready at the moment and exposes, in particular, underlying C binding types to the Rust user. And just kind of clean up, what at this moment, given what we know, what we think the Rust API surface should look like. And then once we're kind of got that API all clean for the things we've already implemented, we'll be in a good spot in the future to go rip through all the remaining queries very fast. So let's go ahead and get to our code. And, chat, remind me if I forget to go back to the code and I'm talking but not showing. Last time I did it 4 times. I was just talking and talking and talking about the code and you couldn't see it. And, bummer. Live and learn. All right, so here's our code and I'm checking and making sure you can see it. Good. And I think what we want to do here, as I usually do, is I just kind of want to run the build steps and remember how to do what we're doing. So I'm going to go ahead and build the C library, the TB client library. And we do that with this TireBeetle specific build command. It's clients:C. And interesting, I already built this last time, so I don't know why it's rebuilding. There's something the build system is seeing as a dependency, probably in the Rust client code, that is not really a dependency of this library. But anyway, there we go, got the library. And here's our Rust client. And we're gonna run the type checker, but we might have left this with a type check failure, we'll see. Yeah, this is the problem we're trying to solve. You can see here in this error message, this is the buff that holds our requests that we're sending, and it's a reference to that buff, and we're trying to not hold it past the creation of this future. This is our method to submit the account lookup request, but there's an error because the lifetimes aren't working out correctly. So we're gonna go fix that first. All right, to do this, let's go look at our code, and I'm going to make sure we have the most recent version of this code, doing a buffer revert there. And first, I notice that this still says account lookup 2. That's because we did a rewrite of this method, but the original no longer exists, so we can just call this account lookup. And then our little temporary test driver, this is account lookup. Let's go type check that. And again, there's our error. Now let's talk through a bit about what I screwed up last time. So here's our method signature right here. And this is a impl of an object or a struct in Rust. So here's our client struct in Rust that holds our underlying opaque handle to the C client in the TB client library. TB client being represented by this import right here. And this is all Rust bindgen generated bindings to C headers. C headers written in Zig. All right, so if we go back and look at our method, this is the method signature, submit account lookup. It's an async function. And what this means in Rust is that this return value is not the return value. This function returns a future of this value. So there's a whole bunch of magical desugaring of all this code that wraps it up into a future. And that means that we're going to return this future that allows you to get a result in the future sometime. And it could be any time in the future. And the client might want to make many of these requests at once, stash them away somewhere, and then go wait on them. It doesn't want to, it's not just going to sit here immediately in a straight line waiting on this future immediately after creating the future, or some code might, but a lot won't, because then you don't actually get any concurrency. So because of that, we want to not force them to hold on to this reference right here. Like as it is, when you create this future, like you saw in the error message, this reference, the future holds this reference, or at least the type system says the future holds this reference. In reality, it doesn't, because we're not actually using this. Let me restate that. In reality, it actually is holding this reference because of the way async functions desugar. And I'll talk about that in a second, but we don't want to force the user to hold this reference, and we don't want to hold this reference, and we don't want to force them to hold the reference, because we want them to be able to reuse that buffer. And because we want them to reuse that buffer, we're already copying this onto the heap somewhere down here, not there, somewhere down here. So we're just immediately taking that slice of operations requests. In this case, the operations are 128-bit integers right here. We're immediately taking that slice they're handing us and bumping it up to the heap and making our own copy. So we should be able to let them just do whatever they want with this reference later after the function returns. But we can't. And the reason is, so what I was trying to do last time was I was trying to put some kind of annotation here to say to the type system, yo, this future here does not hold any lifetimes, or it does not hold that lifetime. Like I wanted to say like, no, not events. Do not hold the event lifetime. And we spent a long time in chat going around and around. Like I thought there was a syntax to say like in an async function, I'm not going to hold this lifetime, but there is not. There's just not a syntax for that. And so the way async functions works in Rust is that they are sugar. They're pure sugar for something more like this. Impl of the future trait, where the output is a something. And this thing, this is saying this is some implementation of the type future, but it's not a concrete nameable type. Just the compiler is going to fabricate that implementation. This whole type is going to just be fabricated from the body of this function. And this type can hold references in it. Like, and when a type in Rust holds a reference, it's got to declare like these are the lifetimes of the things that I'm holding on to. And in impl future or impl traits, it's represented by, plus something, some lifetime, tick something. But when you just write async fun, the desugaring is pretty straightforward. It just assumes, it doesn't let you control what lifetimes you are going to capture. And it doesn't do any analysis of the function body to implicitly decide which lifetimes to capture. It just says, I'm holding on to these references. And that's just it. So if you use the async function syntax in Rust, you hold on to whatever you're passing in. So this kind of suggests to me that like async function is not actually how we want to write these futures. And also suggested to me that maybe, and I'm not an expert on async Rust programming. I do it a fair bit, though not recently. But definitely not an expert. But this suggests to me that maybe async fun is useful for writing application code. But if you really want to present an API to someone else that is well documented and explicit about things like what lifetimes are in the types, maybe you don't want to use the async function sugar. So that's my hypothesis, and that's what we're going to do. So we're not going to use async fun anymore. It's still going to be an async method, but it's just going to be open-coded as returning a future. It'll still work with async await in the exact same way as our previous syntax, but we'll be able to say like exactly which lifetimes we're holding on to. So I'm going to say impl future of, I think it's output. This is an associated type. Output is an associated type. And then up here, we're going to just import that future trait from the standard library. Future. I believe that's it. And then down here, what we got to do, make a few minor changes here. But one thing we can do now, so the way async function desugars is async fun doesn't do any work in the function at all. It just takes the entire function body, wraps it up in a state machine with a struct that is a future, and then returns it. So in an async fun, you don't do any work. No matter what you write in this function, it's not going to do any work. And that's kind of interesting because in our function here, actually, the beginning of this function, none of this is async code. And in fact, we want to fire this off immediately. So if we wrote an async function here, this code would not actually execute until the caller awaited the future for the first time. Then it would start running the state machine and execute this underlying submission of the request. So really, this code is going to be more correct by not writing it as a desugared async fun, but by open coding the impl of future. So, let's bank that knowledge. That's good to note for the future, because we're not doing anything asynchronous in this function until right here. So given that, we have to make some changes to this function to turn it into a future. But what we do is this function now is going to execute all this code as soon as it's called. This is all the setup code for our request. And then right here, we're going to create a future. And the way we do that in Rust is we go async, not async, async, and create an async block. An async block is very much like a closure, but it's, instead of fabricating a closure, it's fabricating a future. And like closures, it has captures. So all the state inside here is going to be wrapped up into a future. And anything that this state uses from up here is going to become a capture, like a closure. That includes any reference arguments that we use. But we're not going to use this argument. And we could even, so this will capture, by default, it'll kind of like make its own decision about how to capture things. Like I think like copyable things will be copied, and references will be referenced. So if we include a reference here, this future will, have lifetime bounds on it. And if that's the case, you can kind of guarantee that like nothing is captured by reference by putting a move here, but I don't think we're going to need that. I think we're probably good. We're not going to be attempting to capture any references here. So we create an async block. This creates a future. And then here, the first thing this future does is wait. So previously, when we're using async fun, our function immediately waited right at the top of the function, just because that's how the desugaring works. It's a very naive and understandable desugaring, so good. I love that. More simplicity in Rust is better. I was reading those docs about how like lifetime elision rules interact with trait objects and impl trait return types, and I was like, oh man. I already knew it was complicated, but just reading all the rules again, I was like, this is tough. This is tough for people to understand. Like hard to remember, right? And that's why the compiler, does its best to tell you when you're making mistakes, because some of these lifetime rules dealing with the intersection of trait objects and anonymous trait types or anonymous trait impls and futures is all very tough stuff. So we create our future here in our async block, and this async block creates a future. And I think by putting it here, we're just going to go ahead and return it from this function. And this is our future. Though we could also write like await here and await for this future, which you might do if you're inside of a desugared async fun. But here we're just returning this block and it's a future. And now if we go up here, we can put trait bounds on this. So like before, we were trying to throw trait bounds at this return type. Now we actually can add trait bounds to this impl trait, impl future. We probably don't have to, but we're going to, just to be explicit, because this stuff is for the documentation purposes. We're just gonna write down exactly what these features capture. But the reason we don't is because there's a bunch of implicit rules about lifetime elision. So each of these references in the arguments have a defined lifetime, but not a named lifetime here. Like this lifetime, they're just anonymous. And the reason we can make anonymous lifetimes is because of the lifetime elision rules in Rust. And they're supposed to be simple, but I always just kind of pray that it's going to work, and usually it works, and then it doesn't work, and I got to go read the docs again like last night. But the way the lifetime elision works in this situation, where we're returning an impl of a trait that has implicit captures, is this self-reference. Because this is a method, this is going to be captured implicitly. this is not going to be captured implicitly. So if we go back to our main test program, let's look at it real quick. Here's how we were trying to exercise this problem. Is we're creating this buffer of requests. We're passing a reference to that buffer. We're like coercing that buffer to a slice and passing a reference to this method. And then before we wait on it, we're dropping the buffer because we want to do something else with that memory. And we want this pattern to be able to work. And if we see our error message here, you can see that it wasn't working because we were accidentally capturing that reference and we didn't want to. But now, I believe, because of what we're talking about there with the lifetime elision rules, and we haven't annotated the lifetimes, but because of the elision rules, how the elision rules interact with impls and impl_trait returns, we're going to capture the self reference, but we're not going to capture this other argument. We can go test that now. I hope I'm right. I hope I'm right. Yeah, I'm right. That's good. Almost every time I hit compile here, it doesn't type check the first time, and that's very normal in Rust. But sometimes you call your shot, and it feels good when you actually think like the compiler and it all works. So I mentioned again that this should be capturing self, but we haven't really proved it with our test program, and I want to just go test that right now. And I also want to mention that that is what I think I want here. I want to capture self, even though we don't need to capture self because we're not holding any references to self. Let's see, is that true? We want this future to outlive the client. So if we don't capture self here, if we don't capture this mutable self, somebody could drop the client and destroy the client. So actually, it's critical that this future holds on to this reference to self. And there's nothing in the type system on its own that's actually going to enforce that because these are bindings to unsafe code. So when you're writing unsafe code or bindings to an FFI in Rust, you got to think about how do I use the lockful nature of the Rust type system to prevent resources being freed from out of order when all I have under the hood is just a bunch of unsafe pointers. So actually what we need in this case is that this future here that we're returning holds a lock on the client. And we can think very easily as Rust borrows as locks. And so this will hold this reference. We want to hold this reference to the client. And all the futures need to be resolved before the client is destroyed. But we haven't proven that. So to prove that, let's do something similar here, and let's just drop the client. Oh, I'm surprised. I thought the lifetime elision rules would force us to hold that self-reference. We need it to not be possible to drop this client until here. And okay, well, there you go. Complicated stuff. That's why we're testing, and we're going to make it explicit in the type signature, the references we're holding. Because I thought implicitly we would capture self inside of this future and not capture events. But right now, we're not capturing either of these. And I am a little confused why. Drop the client, drop the buff. Okay, well, there's got to be something I'm missing here. If we get any Rust experts in the chat, maybe one of them will fill us in at some point. Anyway, that's why we're doing this. We want to explicitly state the references we're going to hold. So here, I think what we need to do then is say, give a lifetime to self, a name to self's lifetime, and another lifetime to events. And in Rust, we want to make sure that these are two separate lifetimes. For the caller, these references are very likely to be uncorrelated. They're not really related to each other in any way. And we don't want to force them to be related. Like we could just call this, A, and then put a single lifetime on these. And that will be fine from our perspective as the callee, but from the caller's perspective, this is creating a pretty big constraint on what they can do with their ordering of their client and their buffers. So these need to be two separate lifetimes. We'll create one called self and one called events. And then over here, we're going to use a new syntax in Rust. And we're going to say plus use tick S, tick E. Oh, and actually, we don't want to use tick E. That's the whole point of the original exercise, is that this lifetime E is something else. So here we can just say self has a named lifetime, and then E is just some anonymous lifetime. Now, this better be capturing the self reference. So our test code again is dropping the client, and this client is a movable type, I believe. Check that. So if this is a copyable type, then dropping is going to be a no-op, basically. This needs to be a movable type for drop to actually do something with the client. So let's go check that real quick. And this is, yeah, it's a struct without any attributes on it. So this should be not copyable. All right, let's run this type check. And precise captures on infiltrate are experimental. Oh, yay. I know this is not experimental. Let's see what version of Rust we have. 1.81 from September. So if we use this feature, we're going to have to note that, like, you got to have a recent version of Rust to use this. And for now, we're going to do that, but there might be reasons. There are other patterns we can use besides using the syntax. And in fact, I'll try to show you at least one other in a second. But let's use RustUp to get a new version of Rust. RustUp update. I wrote this program, RustUp. I mean, I wrote most of this program. That's my pride. Coolest thing I've ever done. Not really. I've done much cooler stuff. Okay, we're installing RustUp, and this means we're going to have to recompile all of our Rust stuff, RustUp, Rust stuff. And just real quick, I want to recompile the C library just to test my hypothesis that from earlier that when we recompile the Rust stuff, the Tiger Beetle build is deciding that it needs to recompile the Zig stuff. Like there's maybe something imprecise in the build system. No, but no. It didn't have to rebuild this time. Okay, it'll be a mystery for a while longer. So now our stable compiler, our active compiler is 1.83 from November. Now we should be able to use that use syntax. And that is not the right command. Cargo check. We got to rebuild everything. Hold on real quick. I might as well clean out our old build artifacts because we're never going to use those again. Cargo will just accumulate artifacts forever until you, so from old tool chains, it'll just keep them lying around unless you explicitly clean them up. And there's a really cool tool called Cargo Clean All that will, here we go. Cargo Clean All. It'll like look recursively through your home directory and just find all the Rust projects and delete all the crap. Junk, sorry. Okay, so here's the error we were hoping to see. Actually, this is not the error we were hoping to. This is the error we were hoping to see, yes. So this is saying, here's our client, which is a non-copyable type. It's an owned struct. We borrowed it to call this method. The borrow is captured in this future that we wait for later, and we're trying to drop the client, but we can't because the future is holding a reference to the client. That's the pattern we want to see and we want to be enforced. But for some reason, when we didn't use this use syntax here, it didn't capture the self-reference automatically. And I expected it to capture the self-reference. And now that I'm looking at this chat, there's another thing to think about here. We would like the caller to be able to issue lots of futures, right? Just future, 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 future from the client. The problem is I have declared this method as mutable. This makes sense to me. Again, we're doing unsafe FFI bindings, so our Rust code is not holding anything to mutate. But when just thinking about the nature of what we're doing, something under the hood is getting mutated, like the Tiger Beetle Zig code is mutating stuff in its client. So this is kind of a signifier that, like, yeah, there's mutation happening here. But if we put this mutable self here, this is going to be an exclusive lock on the client. So I'm not going to be able to call this method twice without waiting in the future. So this is a no-go. That's not the way to do it. And that's how like normal Rust code works. It's like exposing all the mutability all the way down the type tree. But Rust also has a concept of interior mutability where you don't use mutable references, you use immutable references. And internally, you still can mutate things if the code is declared correctly. And again, we're not mutating anything in the Rust code. We're just kind of like defining a safe Rust type for that uses the underlying library. So this is not going to fly like this. This is still going to be safe because, again, the mutation is all happening inside of the Tiger Beetle Zig code, and it is doing the mutation safely. And as long as we are using its API correctly, we can just have the client, the Rust client, just issuing lots of futures at the same time. So we're going to have to do it like this. Interesting thing here, though, this TB client submit self.client. The thing to think about here, though, is whether, first of all, let's not do this right now. Let's get one thing done at a time. But I'll put a to-do here. To-do, not mute. If we make that immutable, we do use that client in this function. Here we are sending the client. What is this here? Client. Oh, okay. This is a closure argument that is not the same client. One of the pitfalls of shadowing. Can't do anything wrong, but like momentarily I was confused about what this client is. This is not the client. Our client is called self here, actually. So we do use self.client here. And if this self.client is using this as an immutable pointer, then we're going to be in trouble because we're not going to be using we're not going to have a mutable reference here to turn into a mutable pointer. But we'll cross that bridge when we come to it. There are ways to solve that. And I don't think it's going to be a problem. Anyway, back to our signature here. We put this use here, and that generates the error that we expect. And again, I'm very confused about why the implicit bounds didn't work here. See, I expected this to be captured implicitly, but it's not. Anyway, we're going to do this. But real quick, I want to show you the old way of doing this, and it's like this. And I think this will work. Yep, okay, still generating the correct error that we're looking for. Still capturing S. There's something wrong with this formulation of implicit or infiltrate captures. I don't understand it. And like the blog posts that introduced that use keyword for this usage of use doesn't really explain it either. It's so complicated. It's just like, go read the issues in the RFCs. But apparently you don't write this anymore. You write use. Great. Okay, so this generates the error we're looking for. So we're going to follow that pattern. And this is interesting because we would like to write tests that this generates the compiler errors that we want it to. But testing compiler errors in Rust is not trivial. There might be some helper libraries that help us do that, but it's not a simple thing to do. But anyway, we've tested that this pattern is the pattern we want. So let's just get rid of this stuff. We can leave the buff there. And we'll commit this. Okay, now that we've got this pattern working, give me 1 second. Just want to check out how the stream's going and take a drink. Look at my background today. It's looking pretty good. I've got this big window right here, and I intend to put a blackout curtain there so I can control the lighting precisely during the day. But during the day, it still looks good, but it's all washed out. It's kind of whatever color the sun wants it to be. But at night, it's kind of, I can control the colors. So I can do, what can I do? What can I do? Oh, that's pretty good. That's pretty good too. So during the day, it's often like this, but at nighttime, I often like a more synthwave 80s vibe. I could be like an aerobics instructor right now. Maybe I'll do an aerobics stream in the future. Not for Tiger Beetle, but Okay, so let's continue. And again, I'm going to switch back to the coding scene, so don't screw up here. Remind me if I screw up. So we have this pattern correct for this function. Let's go ahead and fix this mutable self because we know we don't want to do that. And I think it's not going to give us any problems. I think we're just going to be able to do it. Yeah, okay. And the next thing we're going to want to do is go implement the create account function following the same pattern that we did here for submit account lookup. So let's do that. I'm going to open this tab over here on this side for reference. And I'm going to work over in this left tab so I don't obscure the code with my head. I was doing that last night too. All right, so we're going to take the submit create account and we're going to write it from scratch by cribbing off of both of these, both the old pattern and the new pattern at once. We're going to call this down here. Where am I? I'm lost. All right, pub fun submit create account dose. And we're going to give it a lifetime here. And this is going to return a future of type result of a vec of something. What did we return before? Create account OK. Let's go look at what create account OK was. Because all these request and return result types are kind of not final. They're temporary. But create account OK. Okay, it can either be, yeah, the account was created, or it was an error. And the error is presently just bumping, passing up the underlying C definition of an error, but eventually that'll be a rustdef. So for now, that's probably okay, but I kind of feel like there might be a result payload here that we need to do something with and we're not doing, but we'll keep using that type for now. This is a result of vec of create account OK. And if we go down here to our account lookup, nope, that's not what we want to look at. Account lookup is down here. Get account OK. We want to put a explicit captures of the self type. And then we want to do something in here. And here's our self argument, and events is going to be an array of something. For now, I'll make it array of nil. And I just want to see if this compiles, because at one point in Rust, writing futures, like you couldn't write like an empty future and just put a to-do bang inside of it. It was a type system error. And we found out earlier in this series that with the async fun syntax, the sugared future syntax, you could just put a to-do inside it. And I'm curious if this syntax for returning a impl trait also allows us to just put to do, because the type of this is bang. It's the nothing type. the bottom type. And that generally says like, yeah, this type will work anywhere because actually it's going to panic and not return. But previously this compiler could not handle this pattern, so you had to put some really confusing stuff right here. And I'm curious whether the compiler can compile this or not. I'm probably syntaxing wrong here. What am I syntaxing wrong? Wrong number of these things. Closing angle brackets. Okay, so yep, still has a problem here. It's saying this is not a future. So to actually like put a temporary value in one of these impl futures, like to just put a placeholder panic, you can't do it. And I really wish they would solve that. Like I thought that this was type bang, but seemingly it's not. Seemingly it is type nil, and it relies on control flow to infer that it can't return, which doesn't work when you're trying to synthesize a impl of future. And that's a shame, kind of like a wart in the original implementation of panic, probably. All these panicking macros in Rust boil down to a single intrinsic macro at some point that handles the panic. Yeah, that's a shame. So we can't just type check the method signature, though there is something we can put here to make it work. Like you could write future do nothing. That's not the actual function, but there's some kind of placeholder boilerplate future you could put here. You can probably also put async nothing, async to do. I bet that works. All right, we've learned something here today, chat. That thing I was just complaining about that I've run into, dozens of times and always been complaining about, you just put an async blocker on your to-do and this will compile. Good to know. We're here to learn. Okay, so let's start writing this new submit create account method. And I need to kind of follow both the old pattern here that only supports one operation and the new pattern from submit account lookup that supports both. So I'm going to kind of look at both at the same time. In this case, we're going to create our channel for receiving the underlying results from, because the actual work is happening on another thread. This is a completion message. And this type here is TB account T. This is the type that is, this is the request type. So this is the type that is being passed to us here, actually. And right now we're just going to use the underlying C type, but this has to be changed to a Rust type at some point. And there's our message channel. And now we create the packet. The packet is the thing we submit to the TB client library in order to do the work. And all of this is construction of a packet, and it's boilerplate. It's going to be almost identical for every method we implement. And at some point, we'll do the interesting work of factoring it out and making it generic across the few types that are changing in here. But right now, we're just duplicating. This is probably going to be more similar to this submit account lookup method. So we'll try to crib off that and follow what we're doing there. I'm going to create a callback. And I'm just going to copy and paste this whole callback because this is almost all pure boilerplate. There's just a few places where you have to change a type inside of it. And I've said that before, but I've also missed the things that need to change here. This is a callback, and then let's go ahead and put this to do down here. This is looking indented wrong. Did I do something wrong here? Ah, there we go. So So this callback, these are all arguments to the closure. You can see there's a double indirection on this closure for reasons. Okay, here's all the converting of our own, we're boxing a bunch of data and converting it to unsafe pointers and handing off these heap allocations to the library. And the size of U128 here should probably be something else. This is size of U, oh, look at the right method. This is our old create account method. This is a size of, what are we looking at? Events lin, used to be the payload. Okay. It's going to be size of TBC TB account T. And again, in the old code, we were handling exactly one request called payload here. And in the new code, we're handling multiple, a slice of events. We changed the word payload to events because the underlying library talks about events. Try to keep the terminology consistent. So this is data size events. Okay, so this code is converting the data size required by again, this closure, more context, this closure is the callback when the work is all done. So this is what we're doing to handle the completion of the work. And this is converting from the notion of array length that the TB client understands to Rust's notion of array length. TB client talks about total byte length and Rust talks about element length. Convert to raw parts, and this is probably going to have to be TBC, TB account T, and all these types here that are so tricky to accidentally type the wrong thing, but won't compile if we mess up. These will all be factored down into a generic function someday. What was this? TB packet T, that stays the same. And this all looks samey. Let's keep going to the rest of our packet construction, which is here. More to-dos in our placeholders. So all this code, yeah, is for, wait a minute. What did I do wrong? That's what I did wrong. Where is our let packet? This is not just constructing a callback. We're constructing a callback inside of constructing a packet. That makes sense. A lot of nesting here. Okay, this all looks more or less correct. Why is there so much nesting? Okay, yeah. Let's look at it real quick. This is a block for creating the packet. This is a method called to create a box. The box is a box of a closure. So this is a closure opening here. The closure does a bunch of unsafe stuff, so that's unsafe. So this is, and then we send a message at the end of the closure. So send a message, unsafe, closure. Oh, this is, yeah. Closure, box, callback. Ooh. Something like that. You get it. Something like that. Anyway, it's impossible to get it wrong because of types, but ugh. In HTML, we would probably write like HTML body. Just to try to remember what all this stuff is. Okay, anyway, rest of the packet construction. This is all very similar to, not that, but probably submit account lookup. So here we're going to copy paste what we did before, throw it in there, and just look through any type annotations here. So the events are not U128, they're TBC, TB account T. We're creating accounts, creating some number of accounts. And that all looks the same. And here we are, this is some open-coded conversion of a owned Rust vector to a pointer length pair. So we can hand off ownership of this vector to the underlying library, the FFI library. On Nightly, there is a method explicitly for this because it's a very common thing to need to do. Like the box has a method specifically for this, but vectors apparently don't. So here we get the pointer and we get the length, and then we just say, forget about this vec, it doesn't exist anymore. All right, these types here, this is no longer a lookup account operation. This is a, what operation is this? Create account. And this is where we can really make non-type safe errors. Like there's a bunch of stuff here that we can just get wrong because this is just underlying C enums that are actually just bytes and unsafe pointers that are just anything. So if we screw this up, we really screw up. That's why extracting it to a generic function later will help. Just right at once. This data size is a TBC account T multiplied by the size of the vector. None of this stuff changes. They're just a bunch of zeros. Oh, that's a pointer. That's zeros. And okay, that's the construction of the packet. And this is impl future. And so then down here is where we're going to do this is all construction of a packet. This is all callbacks that are not executing right now. So this code is out of order. Down here, we're going to submit the packet. We can go back to look at our account lookup and crib off that. This code is exactly the same. Submit that packet. And now we start doing our async work. And now we can do an async panic or an async to do, and we can type check this again. Something didn't work. That's easy to fix. Just syntactic. Type check that again. Something didn't work. With line 181. Help a struct with similar name exists. TB account TK. I know I'm going through those error messages really quickly. I just typoed this, and it's telling me the typo. Okay, that type checks. I'm going to checkpoint our work. And again, I should explain this every stream because it looks so sloppy. When I'm just hacking, I don't care about the commit history. I'm just making checkpoints so I don't lose my work. I'll clean it up later. I promise. Okay, so submit the thing. Here's where we write our future. And this is also going to be mostly the same pattern, just same stuff over and over. I'm kind of looking at it real quick. Like this looks like it is mostly the same. This is probably going to change these types here. Let's copy this part. So this is where we wait for the result. So the underlying TB client library is sending stuff to the server and it's getting the message back. And then our closure is running and sending us a message back saying all the work is done. And it's also converting it back to owned pointers so we don't lose them into dangleness. We don't lose them to dangliness here. We don't want to dangle those pointers. Okay, then we pull out the data we're going to need from the message. This is the original packet that we constructed previously. This is just a buffer of the results that have not yet been converted to our operation-specific results. And this is the original events that we copied out of the arguments and pushed onto the heap. This error handling is the basic top-level error handling that is just the same for every single operation. Eventually, we're going to improve that. That is just a placeholder simple error. And then we construct the results. Now, these are type-specific, operation-specific. So in this case, our result is not a TB account T. Our result is going to be, let's go look at the old code for submit account, or create account. So right here is where we're previously interpreting the create account results. The results are TB create account result T, create accounts result T. But now instead of just one, it's a whole array of them. So we're constructing a slice from our results. We're taking a slice, we're constructing a slice of our type from a vector of bytes, just doing an unsafe conversion of the two. This is a TB create account accounts result T. TB create accounts result T. So now we have a slice of the results. And let's go again and go look at our new code for handling multiple lookups down here. And this is the meat of the changes we made yesterday. Hey, Jay the developer, welcome to the stream. My name is Brian, and I'm doing some work on the Rust client for TigerBeetle. TigerBeetle being a new financial database written in Zig. If you came here expecting Zig coding, I apologize for that. Sometimes on the stream we look at Zig code, but we are not writing any today. We're writing Rust code. Sorry about that. Eventually I'll do some Zig coding on this channel too. Matt Clad does Zig coding on this channel sometimes, once a week, or at least talking about Zig, but I'm mostly working on Rust. And in the moment we're working on, yeah, expecting some Zig. I know. I'll show you some Zig real quick. tbclient.zig. Look at this Zig. Oh, it looks similar to Rust on first glance. So this is kind of the library that we're binding Rust code to. It's a library for talking to the TigerBeetle server. And I look at it sometimes on the stream for cross-referencing and understanding what the TigerBeetle is doing under the hood. Oh, it's so beautiful. So beautiful, that Zig code. Have you written any Zig yet, Jay? I got to keep hacking a little here. So what I'm doing is currently rewriting the old submit create account method into submit create account 2. And here's where the big code is going to be right here. I'm just going to go type check this and make sure this at least builds. And I wrote something wrong. TB, okay, this is just another typo. This time it did not give us a suggestion for the right type here. But this is not a accounts result, it's a create accounts result. Jay writes Go. I'm chatting with Jay about Zig and Rust and Go. Jay writes Go. I have not written much Go. I've written some, but don't really know Go. Every once in a while I need to look at some Go and adjust some Go, but I've not had a job where I needed to write Go. And in my free time, I mostly write Rust. So here, this compiles now. No, we don't know. Now it type checks. And here is the code, our new code for the other request that goes and looks at all of the results and figures out the results for every request. So in the Zig message protocol, and as exposed by the TB client, it tries not to return results when it can't. So it assigns a meaning to no result. So, and it's kind of request specific. So for each of these requests they're implementing, we have to kind of do parallel iteration. We iterate through the incoming events or incoming requests, called events in this API, and the incoming and the returned results. We kind of iterate them both at the same time, and we have to look at, like, is this result for this event? If not, like, we know something happened for that event, but it's kind of dependent on what it means for there to be no result. And we don't want to expose that complexity of that parallel iteration to the caller, so we're doing it for them in these methods. And I'm just going to rewrite all this code, not copy paste. So we're going to need, let's see, what have I done here? There's a block here. This is kind of nice. So last episode, I talked about, taking, like chunking out functions into multiple blocks of related code. All of this code is all dedicated to building this result accum. And just from glancing, I know that, like, okay, none of this code is going to matter at some point, and it's all going to be related. So we can kind of go work on this block of code on its own. So I'm going to make another result accumulator. And this could be an iterator and probably will be eventually, but right now it is not. Right now it's a just a vector, just for simplicity. And we're creating create account OK, a vector of create account OK. Is a vector of create account OK. And it's an empty vector, and it's mutable because we're going to be building it up. And then we open the block to do all the work of making this vector. And we need two iterators, one over the input events and one over the results. This is just going to be same code. And then we create a loop, unconditional loop, one of my favorite features of Rust. I even wrote a blog post about it. I love loop. And so we're going to do iteration in step. And the next result is going to be mutable because we might need to hold on to the next result. When we look at the result, we might decide like this result is not the result for the event we're looking at as well. So we have to hold on to it across loop iterations. But here we take our next event. And you might think like we could like zip these together in some way, but there's not an obvious abstraction to me that would let's just zip these together and look at them in a single iterator, because we're going to skip some of them, or we're not going to skip. We're going to skip some from one iterator and we're going to take all from the other iterator. You know, there might be a way to do that, but it's not obvious to me. All right, so this first thing we do is the end. This is the condition that ends the loop. So don't have to do it in the while loop head. And if there is an event, we're going to keep doing stuff with it. This is a destructuring assignment. So we look at this next event. These two iterator results are options. So iterators in Rust, when you call next on them, return an option. And if it is something, we're going to destructure it and keep going on in a straight line as we did in this other function. But if it is a none, then we're done. There's no more things to look at. And we're going to make an assertion about the state of our results as well, because if you've gone through all the events, there's no more results because there can't possibly be more results than events. Break, we're done. Now, if we still have events, we have a bunch of cases to deal with. The first is where we already have a result. So it's possible, it's possible for it to have the same amount of results as events, but we also might have fewer results than events. So the first case is if we still have results to look at. And again, we're doing this destructuring assignment, but it's kind of a destructuring if. And then there's also the case for when this is the none case here. None. Right. To do none. So if we have a result, then we have, again, two cases where, what do we have? Oh, we're going to check whether this result is the result for the event we're currently iterating. And if it is, then we're going to have to do something with that result. But if it's not, we interpolate the empty result. So I'm going to copy the same pattern here and create a local just to name what we're doing here. I'm an advocate of assigning logic to locals to give it, names. For event. So if this is the result, it's for the event. And this logic here is going to be operation specific because we have to look at the sum field of the result. And in this case, we're looking for TB create accounts results. So we probably have to go look at the definition of that. And let's look at the tb_client.h. This header file is C, but generated from Zig. So it's tb create account result. And these are all result codes here. This is not what we're looking for, but just these are errors that can be related to creating an account. tb create account result. And I am not finding the thing that I was looking for. Is it not in this file? Oh, the difference between plural and singular is getting me a lot in this project. This is a tb create account result. This is it. So here they give us this index. This is going to be the index into the array that we're looking at, which suggests that we need more information here because we are iterating, but we are not iterating over the indexes. We're iterating over the items in our events. But this will let us give the index that the result is for into the original array. And in Rust, we can do that by just chaining an iterator and creating an iterator over both the index and the item. So here we can say iter dot enumerate. This is a iterator adapter that gives us a iterator of type event int something like that, usize. And this is a iter of that. Anyway, that's how we create the iterator and get the index at the same time. So here we get the next event, and these destructurings of the event now are actually destructuring of the event and the index. We'll call it event index. If let sum next event break, and interesting, this is unused. So we're cribbing this off of the old code we wrote, and this was unused in the old code, unused here. So we don't actually have to name this. We're naming it now, which is fine. But right now in Rust, we have allow unused on. So when we're just hacking things out and trying to figure out how things work, I don't care about unused values. But eventually, before we submit a PR, we're going to get rid of that, and it'll tell us all the things we forgot to deal with. Let's go back and figure out where we were again. Submit create account 2. So that's the event and the event index. Down here, when we destructure this, we're going to have to do that again. Next event index, next result. And this is interesting. Let's go look at the code we're cribbing off of. Remember, we need that index field off create accounts result. And let's go back to look at this right here. Next result, next event. Okay. I was totally wrong about what I said. These are not unused at all. These are not in scope for this block. These are in scope for the rest of this function. So we have the event index in scope. So we're going to say if next something, next result underscore. This has to be distinguished from this next result because we need to assign to this later. Normally I shadow things like crazy, but we can't shadow this value because we have to assign to the original one. And so I'm using this pattern here that a lot of Rust programmers do not agree with. I'm just calling this next result prime. Visually it's not very distinct. Most programmers would say, give this its own name, like next result. I don't know. That's why I do it. I don't know what to call it. It's next result prime. Next result index equals event index. So we're saying if the result we're looking at is the same index as the event we're looking at, then we know that we need to do something with this result. So if result is for event, we do something else, we do something else. And yesterday, I forgot to write this else when I was writing the original code in the other method. And this is a crazy logic error. Like I did not notice this at all, and the code didn't work when we tested it. Because this is valid syntax right here. I just forgot to write else right here. And I have never made this error in Rust before, but this is just the same as this. It's just opening a block after an if statement. This is the kind of error that the Rust compiler will sometimes warn people about. Like this looks really funky. Why did you do this? It's kind of like a dangling if in C. It's if you don't use a brace in an if in C, you get similar types of errors as this. But I'm guessing people don't make this error that much because I've never made that error before. But it was very confusing. And someone in chat figured it out for me, and thank you. It's been very helpful having people fix my mistakes. Let's do the case where this is not the result for the event. Those are the easy cases. I don't want to have to interpret this result yet. So this case here is, none case. That's a none case. Let's go back to our original code that we previously wrote for this. And submit account. Nope. Yes, this one. So this is the previous code that handled just one result. So if there's no result for this request, it means the creation of success. That makes sense. So mostly we're going to expect account creation to work. And if it works, then the server doesn't have to return any bytes over the wire. So no result means success. And so again, down here, we're going to say, is this a return? No, it's going to push. We're going to push something. We're going to push. All right, remember, we're going to push one of these things. And actually, I'll just copy it. All right, probably going to push the OK. No, we're going to do this. We're going to push this thing. And the pattern for pushing here, I'm just copy and pasting. We're going to push onto the accumulator vec. I could have figured that out fresh. I'm just in copy paste mode. Result accum.push something success. And that is also the case down here. And now this is the case where you have to think. And we might as well go to the remaining easy thing is the end of the function. And look at how deep this nesting is. That's a bummer. But again, we're going to factor out a lot of this duplicated boilerplate code later. So this won't be so deeply nested eventually. All right, I need a drink. Okay, so let's again look at our data type, I think. Our result type in TB client H maybe. Let's think about this. I think for now, because again, as I mentioned before, I'm getting tired. As I mentioned before, we're just kind of returning a lot of the underlying C definitions to the caller at the moment. But really, eventually, when we introduce, when we're fully Rust abstracted, the caller doesn't care about this anymore because we have fleshed out the entire vector of results. And this is just going to be some error code, which is almost certainly what all this stuff is. And this is going to have to be probably a Rust enum. So in Rust, we're going to have to, let's go see. I think the Rust bindings, we have Rust bindings to this file. This is the C API. But I think the Rust bindings do not convert this into a Rust enum. I think it's just integers. And maybe BindGen has options that'll convert it to a Rust enum. But even if it did, we're going to want to define our own enums because these all look gross. This stuff all looks gross. We're looking for TB create account result. So this confusion that I had earlier about plurals and singular names in this API, the result type here is create accounts. The request, the operation is create accounts, but the error enum is create account result. And it makes sense because the actual request may have multiple accounts being, yeah, it makes sense, but I'm struggling a lot with that lately. Okay, so anyway, I was kind of babbling. Yeah, these are all just numbers in Rust, not a Rust enum. Let's go back to our Rust code again. So here, for now, I'm just going to go ahead and push that create account OK, which we did the success case. The error case, we're just going to put this result C struct back to the caller, but we have to convert this into some Rust interpretation in the future. And there might be cases in here we want to interpret specially within the Rust client code itself. But for now, we're just going to punt all that. So we're going to result accumulator, push something, and it's a create account OK error. And where's our thing? Where do we get this? Where did this come from? This is next result. I think that's it. This might be a reference. I think it's a reference we need a dereference. I'm just going to try to compile it and see. Oh, I made a syntax. Yep, that's an assignment there. I made a syntax. No, not a syntax. What am I doing? Forgetting my Emacs keys real fast. I often forget my key combos. Line 227. Next result is nothing. Next result is something. And notice again, chat, it told me exactly what I did wrong there. Line 231. Yeah, definitely nothing called next. It did not tell me the right variable here. Too far away in the Levenstein distance. I think that's right, Levenstein. 231, this is next result. And I did something wrong. Okay, there's a cast needed here because of just the differences between what C wants to. The ABI here uses, specific lengths of integers, but the Rust vectors are going to be, the C API uses specific sizes for its integers, but this is an index into a Rust slice. And Rust slices and vectors and containers and things all use the underlying pointer size integers. They're machine specific. Where is event index? And how did I do this cast elsewhere? I'm just wondering whether I put the cast here or I put the cast over here. Probably do the widening cast here. So we'll say as usize. But let's check what we did previously and see if there's an equivalent for the other method. No, these are already the right size. Next event with usize found, what? Cast that to usize event index. Oh, okay. This interesting. This, when we added this enumerate iterator, it's enumerating over references. No, found a event index. Why is that a TB account T? I probably got the order of the tuple of the enumerated iterator wrong. So the error is down here with this event index from here, and this is next event, and this is the index counter. Event index types. Types are so fun. Useful. Okay, so that all type checks. Now we should probably check that this function works. And the way we're going to do it is go modify our little test program. And we already have a call to submit a count. I'm confident that we're going to get this working. So I'm going to go ahead and clear out all the old code. I don't want it sitting around anymore. So this old submit create account is dead. This is now submit create account. And this stuff is all still more or less being used. But this completion message, we had to create a new version of completion message, but we've done with the old one. So this completion, let's do replace string. Completion message 2 is now completion message. And I think that's all we need to change to promote this to the big game. So let's go over to our main test driver. And this is no longer just one account. This create account operation, are we still using this? No. So both create account operation, originally I wanted to have have some duality here in the API where there's structs defined specifically for the request and specifically for the result. But it's not really making sense to me anymore. And in this new iteration of the API, I have not defined operation types. But we'll see how that goes in the future. So this doesn't exist anymore. This field doesn't exist anymore. And wait, that doesn't exist. This is right. And this all goes into a slice. And we're probably going to want to put 2 here just to see if the multiple operations work. multiple events. And so we'll do second one here, account ID 1 and account ID 2. And these, we'll leave those numbers the same for now. Put a second account here. This is account ID 1. This is account ID 2. And we reuse that account ID down here when we're doing the, so this little test is just creating accounts and then looking up accounts. Account ID 1. And then over here at the end, we'll do account ID 2. So this lookup is going to succeed, fail, succeed, fail, succeed. And let's just see if that checks before we test our code. Cargo check. Okay, so this warning here stems from a change we made like an hour ago. The submit methods on client, so it's saying this binding doesn't need to be mutable. And that's true because our functions here are no longer taking a mutable self. They're taking an immutable self reference. And let's commit this. And now we're going to actually set up and run the real test. Give me 1 second here. Give me 1 second, chat. I seriously mean it. 1 second. I just had to moisturize. Just admiring my view here. Okay, we got to set up the database and get the environment going. So over here in Tiger Beetle land, we are going to run, we already have a database. If you can see, we have a database. This is our test database. We've been using it for a few weeks now. It's already got some accounts in it, and we're just going to run the server, connect to it. So to do that, we're going to say run start addresses. I'm remembering the arguments to the start command in Tiger Beetle. Cluster 0, the path to the file, and I don't know what else. That might be it. Ooh, that is not it. All right, it's saying, oh, unexpected argument cluster 0. I guess I was wrong about that. Doesn't care about the cluster. Invalid, oh. Okay, there we go. And let's go just run it and see what happens. Uh-oh, I did something crazy in my terminal. Cargo run. And we upgraded Rust today, so that's why everything's rebuilding. And I didn't do it right. I did an error. Let's go 145 in our library. This so if there's no next event, this is saying there should be no next result. I bet I forgot to advance the next result iterator somewhere. Let's think it before we go just cheat and look at our previous method. Again, this will all be abstracted out, refactored to lift this into a common function shared by every request at some point. So if we use, so right here, like if we use the result, we got to move on to the next result. So I'm going to say next result equals, and I'm kind of surprised we didn't get a warning about this being mutable if we're never reassigning it. Maybe it did. It doesn't look like it though. next result equals result iter.next. And now let's go crib off the other method and see if that's what we did previously. Right there. Oh, you can't see it. It's under my face. Right there. Right there. Let's try that again. Okay, it at least ran to completion, so that's good. And you can see there were errors. So this is our create account request, and there's errors for both of them. But that's fine because we already had this 21 result code is already exists. And that's what I expected. Now, if we go up to our test program again, and we create some new account IDs, this should both succeed, but we're gonna panic for some reason. Oh, whoa, interesting. I've never seen this before. We did something very bad. So we tried to construct a slice from something. Oh, I know what it is. Okay, so let's look at the, let's get a backtrace, and hopefully this will show us exactly where the error was. So the panic was in the core library here. That's kind of surprising. I would expect this to, the reason, so normally in Rust, when you panic, it says where in your code that the panic was. But this is a very curious error. This is an unsafe precondition. Like this is a custom error message, probably from inside the core library somewhere. Like maybe this is coded in the slice module in the core library. So you might expect this to say panicked at, core source slice something. But maybe this is such a fundamental operation that it's hard coded in the compiler, but probably there's like a compiler specific error that causes it to not show, like maybe they don't want to say internally like what the path to slice from raw parts is or something. But a little bit of a strange panic there. Thread caused a non-unwinding panic. That's interesting. This is such a bad error that I've done that the core library decided that didn't want to even try to continue. Like I screwed up so bad. I've actually never seen this thread caused a non-unwinding panic before. Very curious. But if we go to, it's probably the right thing because I did something very wrong with the pointer here. Interesting. Like, no, in our case, if they just panicked, like we could continue with that panic. But let's go show you what I did wrong. I already have a strong idea that I know what I did wrong. First, before we do that, I wanted to show you what happens if we do a backtrace here. I suspect this will show us where our error was exactly. Oh, we're not going to get the panic because now the conditions for creating that panic no longer exist. So let's go to our main function, create some more new IDs, run with a backtrace. And let's give a look at this backtrace. All right, so this is in the opposite order. So the call stack begins down here. And actually, this is nice. So Rust backtraces sometimes are pretty and sometimes they're not, depending on, the phase of the moon. But here we're starting at this core ops function call once. But in actuality, there are more stack frames down here that the standard library says are not useful for us to see. And we could do this if we really wanted to see them. But here is our program. It's also interesting that so for many years, the standard library forgot how to do this, forgot how to omit the kind of runtime stack frames at the beginning of the stack. And so it printed out a bunch of ugly junk here. And they fixed that at some point. But interestingly, they're showing us the first frame as this call once here. And that's actually, that's still runtime code. They should really be showing us this as the first frame because that's our code, that's our program. So I'm wondering if they're doing this intentionally or if this is kind of a mistake, or maybe it's imprecise in some way. Like figuring out how to exclude these frames was a complicated technical problem apparently. And maybe there's just not a way to exclude this from the backtrace, but really we want to see this as our first frame. But here's a bunch of Tokyo stuff because we're running Tokyo in this program. And this is our actual main function. So this is the main function, except that our main function is wrapped in a bunch of Tokyo stuff. And here's our actual main function, or our program's main function. Then we submit this create account, and right here is where our error is. So lib.rs 128, because here is where we, here's that slice from raw parts unsafe function that we screwed up. So let's look at lib 128. And 128, this is what I messed up. And if we think about what happens, what an empty result is and what an empty vector is, we'll figure out why I screwed this up. So in Tiger Beetle, the Tiger Beetle protocol for this request, if the operation succeeded, you get no result. And both of the operations in our test run were good requests. So they both succeeded, both created accounts. And so then this result slice or vector that we're getting back is going to be an empty vector. There are no error results for us to look at. So it's a vector of nothing. And this result pointer here as a result is going to be what is this pointer going to be? It's not going to be a null pointer. It's going to be a sentinel pointer with a strange value like 4 or something like that, I believe. But this pointer we're not allowed to actually construct a slice out of, it seems, which is kind of surprising. But this pointer in the vec, so an empty vec, when the vec is empty, the pointer is not a pointer to 0. It's a pointer to a sentinel value, leaving the 0 open for like enum packing optimizations. As I recall, I don't remember exactly what it's doing, but I don't believe this will be a null pointer. This will be a sentinel value of some kind. And we're trying to say, this is an actual pointer, and this length is going to be a 0. But apparently we're not allowed to actually construct a slice using that pointer. This is nuclear, this value here. So I'm wondering if there's like some API in the library that'll let me, kind of do this anyway, or if I need to like check for that vec or the length of the vec and have a special case here for that case, which is probably what I'm going to do. But let's go real quick and look at I kind of saying let's go read the documentation for vec and slice and see if it indicates what the representation of this unsafe pointer is in the case of an empty vec. But at the same time, I don't think it's worth it because that's definitely what the error is here. Let's go read the error message one more time. To be aligned and non-null. The total size of the slice is not to exceed that. So the total size of the slice can't exceed like half of a U size for machine reasons. So it's interesting. Like I might have think like the runtime, the core library knows what that sentinel value is for. Well, the core library doesn't know what vecs are, so maybe it shouldn't know. But this error message doesn't quite tell us what we did wrong. It gives us a very strong hint of what we did wrong, but not exactly. But anyway, the thing here that I think we should do, that I'm going to do, and maybe someone will come along later and tell me a smarter way to do this, is I'm going to say if result.len, result is empty. I'm going to say result not empty first, I think. I'll do the empty case second. And then, so if we have stuff in our result, then we construct a slice from the vector. if we don't, there's also probably another way to do this. We could probably say, there's probably a way to do this with something like ask the vector to give us a slice. And then there's probably some method for casting, unsafe casting a slice, like from a slice of bytes, give me a slice of something else. You know, what I've done here is I've just, I've taken that pointer out of the vector and I've manually constructed a slice from it. But I bet there's a method that says like, I have a slice of bytes, give me a slice of something else unsafely. And that would handle this case for me. And I'm kind of wondering if we should go browse, browse the standard docs. Yeah, why don't we just go look for a while? Let's go change our scene. Yeah, Future Highway suggests transmute. And do I want to do that to a slice? You could definitely do it. So transmute is basically the complete unsafe reinterpretation in Rust. Like it says, I've got a thing, just take the bytes of that thing, give me another thing. And in this case, it might work. It would probably work. We'd have to think hard about it. So if there's anything other than transmute, generally I want to use it because somebody else has thought harder about all the different conditions for undefined behavior. But it might be reasonable to do it. Like maybe maybe the alignment is not right, but we're already dealing with alignment issues here because our bytes have to have the same alignment as this. And the underlying Tiger Beetle client library knows that. So presumably this bytes buffer that we're casting to this has the right alignment. But yeah, transmute would totally work here. I don't want to transmute though. But, maybe if we're going to do this special case, it might just be fine to take the slice of bytes and transmute it to a slice of the thing we want. I kind of want to go read the docs though, just to see if there's anything obvious for converting a slice of one thing to a slice of another thing more safely. So let's go do that. And if I take more than 5 minutes doing this, we're going to give up and come back and we'll do that transmute maybe. Nah, we're not going to do that. I don't want to transmute. I don't want to transmute. By the way, I wrote the transmute function. I made that function. I should, yeah, proud of that. That's my pride. Okay, there's my browser over there. What were we doing? We're going to look at the standard library and go to the slice module in core. And it's not here. All we have is functions here. That's not what we're looking for. We want slice type. This is the slice module. This one. And we'll collapse all the details. Yep, I'm to blame for the transmute function. A lot of Rust development subsequently has been like, what other functions can we implement to not have to use transmute? And now there's a whole project in Rust to come up with like a way to do safe transmutes with a clever type system stuff. I don't know anything about that. All I know about is casting. Unsafe casts. Align. Oh, what am I doing? I'm thinking about transmute, so I'm searching for transmute. I kind of want to look for like unsafe. So unsafe, it's going to be an unsafe fun. Align to does not seem correct. Get many unchecked mute doesn't seem correct. Although, what is that doing? It's kind of like a scatter gather thing. Clone to uninit, don't know what that is. Get unchecked, no, we want some kind of like conversion language. Get unchecked, get unchecked, get unchecked. Am I iterating? Am I searching over the same things over and over? These are just implements of various slices, indexes. More stuff as that's some kind of cast. Okay, there's an impl over buffers of U8, and that's what we got. So in Rust, oftentimes, like, there will be specialized methods for doing these kind of low-level systems-y conversions between bytes and other things. So this impl of slices of U8s seems like the place it would be if there's some kind of unsafe cast from a buffer to other things. But it doesn't really look like there is here. There's conversions to ASCII, and that seems about it. So I don't think the thing that I was hoping exists actually exists. All right, we're going to go back to our code, and I'm going to switch scenes. And yeah, maybe during code review. So Alex Kladov, Matklad, works for Tiger Beetle, and he is a very clever person, and he'll probably be the one to review this. He knows Rust better than I do, and he might know a better pattern for doing this. So if it's not an empty result, we're going to do this. Otherwise, we're just going to return a slice and just type in for it. That should work. Let's cargo check that. Yep. That's a very nice pattern. You can just create empty slices as much as you want because they don't actually hold any reference to anything. Kind of magic. Cargo run. And this is going to work because we didn't recreate our scenario where that crashes, where we have new accounts. All right, so this, we're expecting, the thing we were just fixing, chat, is that when we create accounts and all the account creation operations succeed, we were doing an unsafe buffer cast incorrectly, and the compiler, or the core library rather, was smart enough to figure out we were doing that and did a controlled abort. All right, there we go. Let's go look and see if that all succeeded. There's our results for those two account creation operations. Good, no abort. And then here's our subsequent lookup. We looked up account number 1, ID 17. Then we looked up something that doesn't exist. Then we looked up an old account 1. And then we looked up another something that doesn't exist. And then we looked up the other account we created. So everything's working, finally. That's great. All right, so is there anything I want to do with the code before we get out of here? I am not entirely sure. Let's see, how long have we been going? Almost 2 hours. That's pretty good by me. I find that 3 hours I start suffering. 2 hours is okay. Let's go look at our library real quick and just kind of admire our work. All these attributes are pretty admirable. These imports. So we're getting to the point where like we kind of know what we're doing with this API design and binding to the underlying library. And we're kind of getting ready to turn the page and start thinking about cleaning things up and making the API prettier. All these imports, cargo format will handle that at some point. This allow unused, we're going to leave it here for a long time. Maybe at some point we'll remove it and do a cleanup pass, but I don't care about unused right now. This, if you recall from a few episodes ago, is a big problem. 128-bit integers in Rust don't have a stable representation for use in FFI. They don't have a stable ABI for the FFI, at least in the compiler we were using. We switched compilers today. We updated our compiler so that we could use, a new feature. Maybe this has been stabilized. Let's go check it real quick and see what happens if we run the compiler. Yeah, so you can see that compiler does not like us passing Rust 128 bits into C. That's a problem, but we're going to keep dealing with that some other time. We'll deal with that in the future. This is our underlying bindings. This is our client type. We deleted some of these request types that we're not using. These two result types, we're probably going to end up with a result type for every request type. Still expose C types. So probably what we're going to do on the next episode is go through this and start hiding all of the C bindings from the caller. So everything's going to look like Rust from the caller's perspective. So figuring out how we want to handle this type, probably we're going to create an equivalent, maybe a completely equivalent Rust type. Down here, same thing here. We're not going to expose the account type from the C bindings, but the Rust definition will probably look almost the same, if not the same. This client, I don't think there's anything we want to do here. In the future, there's probably more we're going to want to do here, like this addresses is just a string, but it's parsed in a Tiger Beetle specific way into multiple addresses. I don't know what we're going to do with that, but I'm going to punt that for a while. The drop case, I don't know if we've actually implemented it. Yep. So we're just leaking the client. Eventually we're going to want to, oh, wait. Yeah, just leaking. So our drop implementation, our drop trait for client just calls close, and our close method doesn't do anything. So we got to go do that soon. Stuff down here is not all that interesting. That is like this event here. This is a request for account lookup. You just pass in an ID. That's probably not going to change because IDs are just plain old data types. But this request up here, this is probably going to change because this is another C type. So next time we're probably going to go clean up this API like this and make sure these all have a pattern to them, because we're trying to establish the pattern when we're going to use for implementing all the remaining methods. And we're getting to the point where we're pretty confident. Hey, again, Throat Pies, welcome to the stream. If you just joined us, I'm kind of summarizing what we've done here, and we're going to call it quits pretty soon, but I'm glad to see you back again. We've had some very productive streams in the last few days, really starting to hit our stride with this project. And I'm hoping to do, a lot more, and I'm not taking any vacation over the holidays. So I'm hoping to get a lot more done before the new year. So next time we're going to define Rust types for these and figure out how to, like, the patterns we want for the conversions between the underlying C types and the Rust types. And we're probably going to go ahead and factor out all of this code, because now we have two methods that seem to work the way we think they need to work, but the code is almost identical except for, all this setup code for creating the packet just needs some type parameters basically. And this final code for interpreting the results is pretty similar between, we may or may not be able to factor this out. We'll have to look at it. But yeah, I'm really feeling like I want to clean this up and make it look pretty. And after that, then we'll go on and probably pretty quickly implement all the remaining methods. And then we'll kind of be at a point where we can probably submit a PR and announce, this, a preliminary version of the Rust client could theoretically be used, which will be a really nice result to deliver back to the team, since this project has been going on for a little while now, pretty slowly, but it's accelerating. So this is all looking pretty good. Look at how good my background looks today. I'm so happy with this. Is there anything else I need to say to sign off? Okay. Too long now. Yeah. My name is Brian. I stream sometimes on the Tiger Beetle Twitch, currently about the Rust bindings, irregularly, but at some point, maybe soon, I'm going to schedule at least 1 hour a week in a regular time slot to definitely be streaming. And so some people will be able to find me if you really want to watch the stream. I really appreciate everybody who's come and watched the streams and participated and helped me figure out some of these bugs and things. It's really been rewarding, and I appreciate it a lot. My name is Brian. GitHub is Burson, BRSON. If you want to find my socials, they're on my GitHub page, burson.github.io. This has been super fun. Thanks for joining me. I'll see you next time.